All right, good afternoon. My name is Chris Wood, and today we're going to be talking about the p-values and the zero point zero 0.05 significance rule. So, what is a p-value? A p-value, or a probability value, measures how likely it is to observe your sample result, or something more extreme, if the null hypothesis is true. Another definition would be a statistical metric that measures the probability that observed results occurred by pure random chance, assuming that the null hypothesis is true. As mentioned above, a null hypothesis is a prediction of no relationship between the variables that you are interested in, and an alternate hypothesis is usually your initial hypothesis that predicts a relationship between the variables that you're looking at. And the p-values are always going to be between 0 and 1. And the purpose of these probability values are to help researchers determine if a study's results are significant or just random noise or just coincidence. All right, so I found a pretty good example on YouTube real quick that explains it in 3 minutes between p-values, the null, and the alternative hypothesis.
We are going to talk about p-values, an important statistics concept, in 3 minutes. In the 1930s, mathematician Ronald Fisher had a colleague who claimed that she could detect when tea was poured before milk. Intrigued by the claim, he made an experiment on the spot. He made 8 cups of tea. 4 had the milk poured first, the other 4 had the tea poured first. He asked her to identify which was which. Remarkably, she got them all correct. This begs the question, what is the probability she was guessing by random chance? And still got the correct answer. Without deep diving into the permutations and combination math, the answer is 1 in 70, or about 1.4%. Now ask yourself this, is that likely enough to be a coincidence? 1.4% probability? Because that probability is so low, so unlikely, the p-value, we are inclined to think she has a special ability, and she wasn't randomly guessing. More formally, we will call the status quo, where we assume she's randomly guessing, to be our null hypothesis, H0. And that is going to be any p-value greater than or equal to 0.05, if that's going to be our threshold. But if that p-value is less than 0.05, we entertain the alternative hypothesis, H1, that she has a talent. We can therefore reject the null hypothesis that she was guessing. We can then promote the alternative hypothesis. But what about predicting a continuous value, such as a mean that comes from a sample and we're comparing it to a population? Let's say a cold takes 18 days to recover on average, with 1.5 standard deviations as reflected on this bell curve. This normal distribution has an area of 1.0 under it, and we take fractions of that area to find the probability for given ranges. Let's set a p-value threshold of 0.05, leaving only 0.95 area remaining in the middle. Let's say we test out a new drug on a statistically significant sample size of 31 or more patients. They recovered from the cold in 16 days. Did the drug have any effect? Recall that it takes 18 days on average to recover from a cold. This is going to be our null hypothesis. Our alternative hypothesis is that the mean is no longer 18 because the drug did something, whether it decreased or increased the duration of a cold. This is what we call a two-tailed test. Intuitively, we can say that because the drug average recovery time was observed inside this 0.95 area, we fail to reject the null hypothesis. We can't say the drug is having any effect. Let's try a different drug. This one has an average of 14.9 days of recovery. Because it is outside that 0.95 area, we can say this is unlikely to have happened by random chance. Perhaps the drug is doing something, given our 0.05 threshold. But what about the p-value itself? How do we calculate that? So the p-value is going to be anything equal or less likely to the outcome we observed. So 14.9 or less days, what is that area? That is 0.0194. But we are capturing equal or less likely outcomes. We have to capture the symmetrical probability on the other side, where the drug could have extended the cold. After all, our null hypothesis is the mean is 18, and our alternative hypothesis, the mean is not 18. It goes both directions. Doubling that area gives us our p-value of 0.0388. Because that is less than 0.05, we reject the null hypothesis and promote the alternative hypothesis that the mean is no longer 18. To support this channel, please go to the link in the description.
All right, so I found that to be a pretty interesting example. I mean, even as basic as the one in the beginning, talking about the tea and the milk. Just as someone that drinks a lot of coffee myself. But yeah, just a simple example in the beginning, and then I kind of got into a little bit more complex kind of things that I know we talked about for the midterm as well. So brought in some of those themes. But moving on, the it touched on a little bit in the video, but what does the value 0.05 typically represent? This means that we're willing to accept a 5% risk of making a type 1 error. And a type 1 error is rejecting the null hypothesis when it is actually true. So, as a reminder, the null hypothesis is when there's no relationship between the variables that are in question. So, this is also called a false positive. 0.05 is used because it's just the traditional standard used in many fields. It balances caution to practicality, and it's a convention, not a law. So, as an example, as another kind of short, quick example, suppose a company tests whether a new training program improves employee performance. In this case, the p-value would be 0.02. And since zero point zero 0.02 is less than our 0.05, we reject the null hypothesis since there is statistically significant evidence that the training program improves performance. So I hope these kind of couple examples and the explanation kind of explained it kind of well and thoroughly with some simpler and a little bit more thorough examples. So thank you for your time. I appreciate you watching. And if you have any questions, please let me know. And I wish you the best of luck with the remainder of your classes.